The title of this video is Calibrating Spray Equipment Using Shortcut Methods. Calibrating spray equipment can be a daunting task, with algebraic equations to memorize, different types of equipment to maintain, and often new technologies which may make it seem like calibrating a newer sprayer is a waste of time. This video will offer attendees a quick and easy approach to calibrating multiple types of spray equipment while discussing the pitfalls and remedies. One common mistake instructors encounter is delving into calibration techniques without truly defining calibration to the audience. Calibration is to ensure that your equipment is applying the correct amount of pesticide material uniformly over a given area. We must determine solution delivered over a given area to understand the total product and diluent to add to a spray tank. Diluent is the carrier added to the spray tank, which the pesticide product dissolves. In most cases, this is water. Output, or total solution, is often expressed in gallons per acre on most ag pesticide product labels. A pesticide product label contains the required pesticide product rate. However, it often will have a required output of gallons per acre in a range format. Without understanding the output of your sprayer, an applicator can't determine the amount of product or solution to add to the tank. We often hear applicators say, "You can't calibrate a backpack sprayer." They are half correct, as it can be difficult to calibrate a backpack sprayer due to individual speed variance from across individuals and pressure variance that depends on the user's consistency. However, you can calibrate a backpack sprayer if you follow some simple steps and watch your consistency. To not calibrate a backpack sprayer is far worse, as guessing how much product to add to a spray tank may result in a product delivery that is often over the pesticide product label requirements. This often results in an unnecessary pesticide cost and at times damage to non-target grasses. Damaging non-target grasses often result in invasive weed introduction in consecutive years and the need for constant spray applications. Conversely, product delivered that is below the product rate often results in poor efficacy, loss of time, and money in pesticides. Calibration will ensure your spray application is precise, cost-effective, and avoids non-target burn down. There are few exceptions when determining the output of your sprayer may be necessary. If the product label doesn't have an output requirement, and the product label only requires the product to be added in a per gallon format, or what is termed a concentration format, calibration may be unnecessary. The concentration approach is very inaccurate and only approved for a few non-selective ag products, and many over-the-counter, ready-to-use formulations. Applicators should still check their pesticide equipment once per year to assure all components are working properly. Newer technologies often have flow regulators that deliver the calibrated rate live to the pesticide applicator. This can be adjusted digitally. It may not be necessary to calibrate multiple times per year, but applicators should occasionally check to ensure that their equipment is running properly by comparing the digital readout to a manual calibration approach that we will demonstrate in this presentation. Flow regulators, speedometers, worn equipment, and nozzles and screens that occasionally break, thus presenting incorrect information to the applicator, necessitates the need to calibrate your sprayer at least occasionally. Applicators often ask how many times they should calibrate their sprayer. The answer is, at minimum, once per year in the spring after winter storage. Winter storage can result in corrosion in the lines, screen and nozzle plugging, and damage to tanks. Just because your equipment is working fine in the fall does not mean it will be working fine the following spring. You should take a little time to ensure the equipment is not damaged, nozzles and screens are working properly, and the equipment is delivering the proper output. At times, it may be necessary to calibrate more than once per year. This would be necessary if you change your spray pressure, change your nozzles, change your boom height, or change your field speed. Another reason it may be necessary to recalibrate pesticide equipment is if using multiple products throughout the season with varying output requirements. For instance, If the first product required an output of 5 to 20 gallons per acre, and the second product required an output from 30 to 50 gallons per acre, it would be necessary to recalibrate the equipment to an output between 30 to 50 gallons per acre prior to applying that second product. Applicators refusing to recalibrate their equipment in this scenario would often lose efficacy even if applying the proper amount of pesticide product per acre. This is due to insufficient coverage delivered from the first calibrated rate of 5 to 20 gallons per acre, when the second product requires a much higher output of 30 to 50 gallons per acre. As mentioned earlier, calibration is a chance for applicators to double-check their nozzles and screens. In this illustration, one can view the uniform spray pattern distribution offered by new spray tips on the left image. However, over time, nozzles will deliver the uneven spray pattern that can be viewed in the center image. This is often due to worn spray tips that vary according to nozzle material used. For instance, applicators will often see a change in flow rate if using brass nozzles over a period of less than 4 hours of use, while hardened stainless steel will last much longer. However, applicators should keep in mind hardened stainless steel is more expensive. Plastic nozzle tips are often a nice middle ground that will be relatively inexpensive, yet can carry most applicators through a season. The image on the right illustrates damaged or plugged nozzles. The uneven spray pattern illustrated would be unacceptable for an application, as the applicator could be delivering 2 to 3 times the product rate in some portions of the spray pattern, and 1/2 to 1/3 the rate in other portions of the spray pattern. By calibrating spray equipment once per year, applicators can check or replace all nozzles and screens prior to an actual spray application to avoid these costly mistakes. For this presentation, viewers may follow along using a variety of MSU Extension publications. One Mont guide, titled Calibrating Ground Sprayers Using Shortcut Methods, covers the calibration of sprayers using the no-math 128th an acre method. This is a free publication that can be printed easily from home. 2 pocket guides are also available for a small fee to MSU publications. These are in color, water resistant, and do not tear easily. However, they are specialized into 2 publications. The first pocket guide focuses on calibrating boom and broadjet sprayers, while the second pocket guide focuses on the calibration of hand sprayers. All resources can be accessed on the MSU Pesticide Education website at www.pesticides.montana, and that's spelled out, .edu by selecting Publications and Resources. When calibrating spray equipment, you will need only a few supplies that are often available at home: a stopwatch, measuring tape, measuring container that measures in ounces, pencil and paper, and source of fresh water. In Section 1, we will focus on calibrating hand sprayers using the 128th an acre method, otherwise known as the no-math shortcut method. It is termed the 128th an acre method as there are 128 ounces in a gallon, so that by applying product to a test strip that is 128th an acre, you can easily convert ounces directly to gallons per acre without any algebra or conversions. Prior to calibrating a hand sprayer, you should always ensure your hand sprayer is clean prior to use. If in doubt, always assume the sprayer is dirty. By taking time to clean the sprayer lines, tank, and exterior with a heavy detergent, you can ensure safety while calibrating the sprayer. You should also pressurize the system to check for leaks prior to wear. Backpack sprayers are known for leaking due to loose fittings, cracked housings, often after little use. Upon checking to ensure the system is clean and not leaking, you can begin the process of calibration. Simply fill the sprayer half full of water and pressurize. If no leaks are observed, applicators can begin calibrating their sprayer. This is a good time to check and at times replace worn nozzles and screens. Applicators can easily check spray patterns on pavement or dry soil prior to calibration. You should ensure that the spray pattern is even and consistent while gauging the proper distance of the nozzle from the spray canopy to obtain a desired spray pattern when using hand sprayers. If using an adjustable nozzle, a Sharpie can be used to mark where an adjustable nozzle is set once desired spray pattern is obtained. When calibrating hand sprayers, always use the same nozzles and filters as when spraying, so replace nozzles and screens if needed prior to calibration. First, you should measure an 18.5 by 18.5 foot area. This is the test plot and equals 128th an acre. You must ensure that the plot size equals 18.5 by 18.5 feet or the shortcut method to calibrating the hand sprayer will not work. Ensure that the test plot is in an area that is similar to what you wish to spray. If spraying over dense forage, it may be necessary to apply a dye to the tank, as you must apply a uniform spray pattern that is only delivered within the test plot. Applicators may use flags, rocks, or marking chalk, as long as you can view the boundaries of the test plot while spraying. Next, you should time how long it takes to spray the plot with water, while ensuring you are applying at a consistent pressure, using a consistent arcing motion and consistent speed. Spray the test plot 3 times and convert each time to an average. Applicators should disregard any times that are considerably off of average and repeat as necessary. If the spray is delivered outside of the test plot or is applied in a non-uniform fashion, you should repeat the test spray application. Finally, spray into a container for the average time it took you to spray the test plot. What you collect in ounces is the gallons per acre output of the hand sprayer. This simple-to-use technique is much better than guessing the output of the sprayer and will ensure efficacy while eliminating non-target damage from over-application. It may be quite difficult to ensure consistent pressure with hand-operated systems. You may get around this by purchasing battery-powered backpack sprayers, or at minimum, purchasing a spray management valve that can be installed into the spray system. These valves will ensure pressure is delivered only if within the pressure range chosen by the applicator, while costing only $15 to $20 per valve. The following video will demonstrate the shortcut method to calibrating a hand sprayer. Pay close attention to how the video ensures consistency.
Have you ever wondered how to know how much pesticide you're applying when using a backpack sprayer? Are you putting down too much or too little? Well, calibrating your backpack sprayer ensures the proper quantity of pesticide is applied, therefore making sure that you're not over or under applying. That, in fact, saves you money. It also lowers environmental impact by ensuring only the right amount is used, which also lowers the chance of developing pest resistance. Some people may ask, why do I need to calibrate my backpack sprayer if I'm just spot spraying weeds? Spot spraying means you are individually targeting each weed plant and not broadcasting the herbicide. Look at the 2 pictures above. The picture on the left shows an area of high density of spotted knapweed, and the picture on the right shows low plant density. What if these are in the same pasture that you're treating? Are you going to spot spray each plant in the high density area? Probably not. Most likely you're going to broadcast spray the area. You'll be applying a different quantity of pesticide if you're broadcasting versus spot spraying. Consequently, this emphasizes the need to calibrate your backpack sprayer. This episode shows you step by step how to calibrate your backpack sprayer through the shortcut method. For the shortcut method to calibrating your backpack, also known as the 1/128th method, the tools you'll need include a container calibrated to ounces, a stopwatch, a measuring device, and some method to mark the ground such as flags like these. The first step in this shortcut method you'll want to measure off an area that is 18.5 feet long by 18.5 feet wide. This represents 1/128 of an acre. Using your measuring tool and your markers, you'll be able to accurately mark off the right size area for this method. Now that you have your area marked, you're ready to time the spray. To do this, fill the backpack full of water. Begin spraying the area at the speed you would normally and comfortably spray, while timing how long it takes to spray the entire 1/128 of an acre. Keep consistent pressure. When finished, record the time it took to spray the area. Now if you're having trouble seeing where you sprayed, add some dye to the water to help. Now you'll repeat this process of timing how long it takes to spray this area. Do this 3 times. When finished, calculate the average of all 3 recorded times. After you have averaged the 3 times, spray into your calibrated container, labeled in ounces, for that average time. In this example, 1 minute, 25 seconds was our average. The collected fluid ounces represents the number of gallons per acre your sprayer is delivering. In this example, we collected 64 fluid ounces, which means at that speed and pressure we would be applying at a rate of 64 gallons per acre. Now that we have the gallons per acre, we can now calculate how much pesticide to add to your backpack sprayer. Divide the amount recommended on the product label, amount per acre, by the gallons per acre of your sprayer. This total will give you the amount of pesticide to add per gallon of solution. In our example, our product label recommends an application of 5 pints per acre. Convert pints into ounces. 1 pint equals 16 liquid ounces, so 5 pints equals 80 ounces. We divide that by 64 gallons per acre, and this tells us we need 1.25 ounces of solution per gallon of water. So if your backpack sprayer holds 5 gallons of solution, you would multiply the ounces per gallon by the size of your tank. In this case, you would add 6.25 ounces of product per tank. So as you can see, calibrating your backpack sprayer is an easy process using this short 4-step method. Mark the area, time the spray, measure the application, and calculate the quantity of pesticide needed.
In this section, we will discuss using the shortcut methods to calibrate boom sprayers. Boom sprayers can be recognized easily as they have multiple nozzles along one boom. There are many types of boom sprayers, including ATV, tractor, or truck-mounted sprayers. You must determine proper boom height from the spray canopy. This distance is determined by the distance between the nozzles, spray pattern angle of nozzles, and overlap required. Most non-flood type nozzles are rated at a 30% overlap. This is because most flat fan nozzles emit less flow rate at the nozzle edges. To compensate, most flat fan nozzles require a 30% overlap, but always read the nozzle specification sheet if available. A second type of nozzle, known as a flood type nozzle, requires 100% overlap for high output applications. Flood type nozzles are often used with liquid fertilizer applications. One rule of thumb can be followed if applicators are using a nozzle emitting a 73-degree spray pattern and a conventional 30% overlap is required. The rule of thumb states the distance between the nozzles is the same distance you should set a boom from the spray canopy. This rule of thumb does not apply to nozzles with differing spray angles. It should be noted that you may reduce drift by using nozzles emitting a broad spray pattern as opposed to nozzles emitting a narrow spray pattern. For example, An applicator using nozzles emitting a spray pattern of 65 degrees must set their boom at a distance of 22 to 24 inches off the spray canopy, as you can see in column 1. Whereas if using nozzles emitting a spray pattern of 110 degrees, applicators may set the boom only 10 to 12 inches off the spray canopy, thereby reducing drifts significantly. Booms may be raised to increase overlap of nozzles or lowered to decrease overlap of nozzles to desired overlap. Next, we will discuss pre-calibration step 2 when calibrating boom sprayers. This step is to ensure the boom is level while offsetting the nozzles by 10 degrees. A 30% overlap causes spray patterns to collide, otherwise called interference. If nozzles are installed parallel with the boom, we see more interference. Interference causes an uneven spray pattern distribution and should be eliminated. By offsetting the nozzles by 10 degrees, you can eliminate interference. As this picture illustrates, ensure the nozzles are offset by approximately 10 degrees and are consistent across the boom. Pre-calibration step number 3 is testing the uniformity of the nozzle flow rates. This step gives you an opportunity to check spray patterns for uniformity and assess the flow rate of each nozzle. Nozzles should be delivering a uniform flow rate. The average nozzle flow rate across the boom can be estimated by checking each nozzle flow rate after 1 minute of use. This can be determined by placing containers under each nozzle and collecting liquid for 1 minute at the pressure that would be used while spraying. If any nozzle falls outside of the 10% error range, that nozzle should be replaced or inspected for plugging. Many nozzles can be cleaned by using a toothbrush or washing in a bucket of water. The test should be repeated until each nozzle's flow rate is within the 10% range across the boom. In this example, an applicator should determine the average flow rate of nozzles across the boom. The applicator has 4 nozzles. Nozzle 1 emitted 50 ounces, nozzle 2 emitted 48 ounces, nozzle 3 emitted 46 ounces, and nozzle 4 emitted 48 ounces. To obtain the average flow rate, each nozzle's flow rate should be added together and divided by the total number of nozzles. In this example, the average nozzle flow rate would be 48 ounces across the entire boom. The applicator should then determine 10% of the average by moving the decimal place 1 space to the left. In this example, 4.8 is 10% of 48 ounces. Next, the applicator should add 10% to the average and subtract it from the average to determine the 10% error range. In this example, the applicator would add 4.8 to 48 ounces to determine an upper range cutoff of 52.8. while also subtracting 4.8 from 48 ounces to determine the lower range cutoff of 43.2 ounces. Any nozzle flow rate between 43.2 and 52.8 would be okay. If any nozzle falls outside of this range, it should be inspected, replaced, or fixed before repeating these steps. An optional pre-calibration step that may assist your equipment in delivering the sought-after output uses the 5940 equation. This equation does not need to be used by pesticide applicators, but is a useful tool for determining ideal field speed to deliver a predetermined GPA for boom or boomless sprayers in one attempt. The 5940 equation can deliver ideal field speed by taking the gallons per minute flow rate of the nozzle, or GPM, and multiplies this number by the constant 5940 to deliver the numerator. This numerator is divided by the denominator, which is the gallons per acre output of the sprayer, which is multiplied times W, which equals the nozzle spacing in inches. In this example, the pesticide product label requires 10 gallons per acre, and the applicator must calibrate his equipment to deliver 10 gallons per acre when calibrating his sprayer. To use this equation, he must measure the output of his nozzles in 1 minute and convert to gallons to deliver gallons per minute. In this instance, he collected an average 0.2 gallons per minute from his nozzles. Next, he measures the distance between his nozzles in inches. In this example, his nozzle spacing is 24 inches. Then he plugs in this information. 0.2 gallons per minute times 5940 equals 1188. 1188 is divided by the denominator. The denominator is 10 gallons per acre, which was on the product label. Multiplying this times a nozzle spacing of 24. 10 times 24 equals 240 for the denominator. The applicator must divide 1188 by 240, which equals an ideal field speed of 4.95 or 5 miles per hour to deliver 10 gallons per acre. If the equipment is working properly, the equipment should deliver 10 gallons per acre. Once again, the pre-calibration steps are setting the proper boom height, offsetting nozzles by 10 degrees, and testing the uniformity of the nozzles. Once the pre-calibration steps are finished, you can calibrate your boom sprayer using the shortcut methods. Feel free to use the Mont Guide table on page 2 for referencing the proper course length. The course length is critical as this is the 128th an acre method. To obtain the proper course length, you should measure the nozzle spacing in inches. If you measure a nozzle spacing of 40 inches, your corresponding test strip would be 102 feet, as you see here. You can use flags to mark the start and finish of the test strip. Next, you should drive the course test strip at the gear and RPM you will use when spraying, and time. You should repeat this 3 times and take the average. Let's say the average time to drive the course test strip is 90 seconds. You should always be wary of the terrain you will be spraying when setting speed, as you must drive the same speed when spraying as when driving the test strip. Next, you should collect liquid from one nozzle for the average time it took to drive that test strip. In this example, it took 90 seconds to drive the test strip, so you should collect liquid from one nozzle for 90 seconds. Finally, the ounces collected from that one nozzle equals the gallons per acre output of the sprayer. In this example, you collected 20 ounces, so your equipment is delivering 20 gallons per acre. In this next example, you finished all pre-calibration steps and wish to begin calibration. You have 18-inch spaced nozzles and 6 nozzles. What should you do next? You can easily use the Mont Guide on page 2 to reference nozzle spacing with the proper course test strip. Pause the video if needed. For an 18-inch nozzle spacing, the course test strip distance is 227 feet. You then set your 227-foot course test strip and time how long it takes to drive at the gear and RPM you will be using when spraying. In this example, it took 30 seconds to drive the course test strip. This was an average after 3 attempts. What should you do next? You should collect liquid from one nozzle, not all nozzles, but one nozzle for the same amount of time it took to drive the course test strip. In this example, you collected 15 ounces in 30 seconds. What is the GPA? The GPA, or gallons per acre, output of your sprayer is 15. What you collect in ounces is the gallons per acre output of the boom sprayer. This video will demonstrate how to calibrate a boom sprayer using the shortcut methods. They take a slightly different approach by not testing the uniformity of the nozzles prior to calibration. However, this video will provide additional clarity of the overall method.
How to calibrate your sprayer. You will need a large measuring tape or wheel, a measuring bucket, 2 markers, a tape measure, a timer or smartphone, gloves, and a toothbrush to clean your nozzles if you discover they are clogged. After your tank is filled with water, measure the distance between each nozzle to determine the length of travel distance. There is a quick formula that tells you how far you should travel based on your nozzle spacing distance. In this case, it's 20 inches. That means we should travel 204 feet. 16 inches equals 255 feet. 18 inches, 227 feet. 22 inches, 185 feet. 24 inches, 170 feet. As a general rule, make sure your boom is roughly the same height off the ground as the distance your nozzles are apart from each other. In this video, our boom should be about 20 inches off the ground. Mark the distance with flags or between fence posts. A tape measure capable of measuring farther than 200 feet will make this step easier. Driving the sprayer at your intended spraying speed, time how long it takes to travel between the marked distance. Repeat this procedure and average the two measurements. In this case, it took us 33 seconds. With the sprayer parked and the nozzle flowing, set the ideal or intended pressure. Once your pressure is set, catch the output in a container marked in ounces for the same amount of time it took to drive the marked distance. We captured water for 33 seconds, which filled our measuring pail up to 16 ounces. Follow this same procedure on a few different nozzles and calculate the average nozzle output by adding the individual output of each nozzle and then dividing by the number of nozzles tested. In this case, our nozzles were consistently putting out 16 ounces of water. If there is more than 10% variance between the output of each nozzle, you may need to replace or clean the nozzles as they can get ruined or clogged from buildup of chemicals. A toothbrush works perfect for cleaning. If you have any clogged or ruined nozzles, you will need to repeat the timed liquid measuring process once your nozzles have been cleaned or replaced. Use the information you recorded to analyze your results. The ounces captured per nozzle equals the gallons per acre application rate. In this case, we captured 16 ounces, giving us an application rate of 16 gallons per acre. If the gallons per acre rate is not within 5% of the intended rate, you will have to adjust the pressure you spray at or the speed you travel. Repeat steps 3 to 7 to recalculate this. Your sprayer should now be successfully calibrated.
In Section 3, we will cover the calibration of broad jet or boomless sprayers. This type of nozzle is more robust and provides a 5 to 30 foot swath from one nozzle. These nozzles are used in areas of rough or uneven terrain such as right-of-ways, hillsides, or rangeland containing rocks and other obstacles. Calibrating broad jet sprayers generally follows the same approach as calibrating boom sprayers with a couple easy differences. First, you must determine test strip distance by measuring the spray swath of your broad jet in feet. You can obtain the course test strip distance by taking the constant 340.3 and dividing by the broad jet swath width, which in this example is 30 feet. Then multiply whatever the answer is by 10 to obtain a course test strip distance. In this example, you must take 340.3 and divide by the spray swath distance of 30 feet to obtain 11.34. As mentioned prior, 11.34 must be multiplied times 10 to obtain the 113.4 feet course test strip distance. Next, you must drive the test strip at the gear and RPM you will use while spraying. You will do this 3 times and take the average, which is in this example 25 seconds. Next, you collect liquid from the broad jet for 25 seconds, or the amount of time it took to drive that test strip distance. In this example, you collected 130 ounces in 25 seconds. Finally, you would divide what you collected by 10 to deliver the GPA. By dividing 130 ounces collected by 10, you calculate your broad jet is delivering 13 gallons per acre. So, the only differences between calibrating the boom and broad jet sprayers is multiplying times 10 to obtain course test strip distance and dividing the ounces collected by 10 to obtain the total output in gallons per acre if calibrating broad jet sprayers. Let's try to calibrate another broad jet that is emitting a 25-foot spray swath width. Feel free to stop the video when needed and consult the MSU Extension resource you may be using. How do you determine course test strip distance if the spray swath is 25 feet? You must divide the constant, 340.3, by the spray swath distance in feet. 340.3 divided by 25 equals 13.6. When calibrating broad jets, this answer must always be multiplied times 10 to deliver the test strip distance. In this example, 13.6 times 10 equals a 136-foot course test strip. You then must drive the course test strip at the gear and RPM you will be using while driving. While timing. You then should repeat this 3 times and obtain an average, which in this case is 27 seconds. What should you do next? You should collect liquid in ounces from the broad jet for the same amount of time it took you to drive the test strip. You collect 200 ounces in 27 seconds. What is the gallons per acre output of this broad jet sprayer? By dividing by 10, the output of this sprayer is 20 gallons per acre. If the calibrated output is not what is desired, you can 1. Adjust speed, 2. Adjust pressure, 3. Change your nozzles, or 4. Change nozzle spacing. For huge changes to the output, you may wish to change nozzles. By changing nozzles and working with a nozzle specialist, you may purchase a nozzle that targets an ideal output. For most circumstances, you can adjust speed to effectively hit a target output. By cutting speed in half, you can double your output, and conversely, by doubling speed, you can cut output in half. Pressure is less effective at changing output than speed, and should only be used for slight adjustments in output. For instance, you must quadruple the pressure to double the output, or you must cut the pressure by a fourth to cut the output in half. Pressure should never be adjusted to the extremes, as pressure too high often results in fine droplets, excess drift, and loss in pesticide through volatilization. Pressure too low for a nozzle will result in an inconsistent spray pattern and little coverage. In Section 4, we will describe how to determine the proper amount of solution and product to add to your spray tank. Previous sections focused on determining the total product, or total output, or gallons per acre of your spray equipment. It is easy to determine solution and product to add to a tank once the GPA is known. You can easily determine the total solution to add to the spray tank if acres to spray is known. By multiplying acres times the gallons per acre, you can determine the total solution needed for this spray application. In this example, you wish to spray 10 acres with a sprayer calibrated at 30 gallons per acre. How much solution would you need to cover this area? By taking 10 acres and multiplying times 30 gallons per acre, you can easily determine you would need 300 gallons of solution. You can also determine the total product to add to the spray tank with the following equation. You can take acres to spray, which in this example would be 10 acres, and multiply times the pesticide product rate, which in this example would be 2 pints per acre. By multiplying 10 acres times 2 pints per acre, you determine you will need 20 pints of product. There is another equation that is useful if acres to spray is unknown. This is often used with backpack sprayer or hand sprayer applications. The pesticide to add to a spray tank per gallon can be determined by taking the pesticide product label rate, as long as it is in a per acre format, and dividing by the calibrated rate of the sprayer, or GPA. In this example, you are mixing 3 gallons of pesticide solution in your backpack sprayer. You have a product label rate of 3 ounces per acre and are calibrated at 30 gallons per acre. How much pesticide product do you need to add to the spray tank to deliver 3 ounces per acre with 3 gallons of solution? To obtain the pesticide to add per gallon, you must divide 3 ounces per acre, or the product label rate, by 30 gallons per acre to equal 0.1 ounces per gallon of solution. You wish to mix 3 gallons of solution, so you would multiply 0.1 ounces per gallon times 3 gallons, which equals a total 0.3 ounces of product needed for this spray application. Let's review a few calibration scenarios. You're using a boom sprayer with a calibrated output of 20 gallons per acre. You are also using Warrior 1E at the 2 ounce per acre rate. You need to spray 300 acres. Question 1. How much spray solution will you need? Feel free to pause the video as needed. By taking acres and multiplying times the calibrated rate of the sprayer, 20 gallons per acre, we determined the need for 6,000 gallons of solution for this application. By using the same story problem on question 2, how much product do you need? By taking acres, which in this case was 300 acres, and multiplying times the product rate, which in this case was 2 ounces per acre, you can determine the need for 600 ounces of Warrior for this spray application. Question 3. You have finished all pre-calibration steps and wish to calibrate your boom sprayer using the shortcut methods previously described. You have 20-inch spaced nozzles and travel the shortcut method test strip distance of 204 feet in 25 seconds. You then collect 10 ounces in 25 seconds from one nozzle. What is your GPA? This boom is delivering 10 gallons per acre. Question 4. What width and length would easily qualify for using the shortcut 128th an acre method for calibrating your backpack sprayer? Answer: 18.5 by 18.5 feet. Question 5. Your hand sprayer is calibrated at 10 gallons per acre. You are applying Tordon at 20 ounces per acre and wish to mix up 4 gallons of solution. How much product do you need? Remember, by taking the pesticide product rate and dividing by the GPA of your sprayer, you can determine the pesticide to add per gallon of solution. You may wish to pause the video. Answer: you can take the product rate of 20 ounces per acre and divide by the output of the sprayer, or 10 gallons per acre. This would equal 2 ounces of pesticide product per gallon of solution. You wish to mix 4 gallons of solution, so you must multiply 2 ounces per gallon by 4 to equal a total 8 ounces of pesticide product for this 4-gallon tank mix. Next, let's use an actual pesticide product label to answer a few calibration questions. You may wish to pause this video to download the associated story problem packet, which includes story problems on page 6 and the associated Gramoxone product label on pages 8 through 13. This can be downloaded at pesticides.montana.edu by selecting Publications and Resources, then selecting and downloading the core topic story problem packet. These are the questions you should see on page 6. Once again, feel free to pause the video until you are finished. Answers to number 1. What is the minimum GPA required to manage weeds in Mr. Greenwood's scenario? Answer: the product label states on page 12 under spray volume that the minimum is 20 gallons per acre. This is because Mr. Greenwood's weeds are greater than 6 inches tall. Question number 2. What is the maximum product rate Mr. Greenwood can use? Answer: the pesticide product label states on page 13 under grasses for seedbed preparation that the maximum product rate is 4 pints per acre. Question 3. How much total solution and product does he need to cover this area? Answer: by taking 20 gallons per acre and multiplying times 10 acres, we determine he would need 200 gallons of solution. To determine total product, we multiply 10 acres times the product rate of 4 pints per acre. He would also need 40 pints of product for this spray application. That concludes the video on calibrating spray equipment using shortcut methods. If you have any questions or seek further resources, email us at pesticides@montana.edu or navigate to pesticides.montana.edu for further information. Thank you.